about matrices, and I will start with a simple example of a system of linear equations. So it can be one of the systems that we solved last week. For u minus 6v is -2 and -2u plus 7v plus 2w is 9. And we can use a much more compact version of writing the system of linear equations. So we can separate these coefficients that are in front of variables and variables. So in front of the coefficients in the first equation, we have 2, 1, 1. Then we have 4, -6, 0, 7, and 2. And then we can write the unknowns, so u, v, and w. And the right side, at the right side, we have 5, -2, and 9. So that's the alternative way of writing this system of equations. So we can see as these two systems are equivalent, so we can find what is the rule of multiplication of matrix by a vector. So we can see that if you want to multiply matrix by a vector, you can see that each element of the resulting vector is a dot product of a row and this vector. So the first element have to be equal to the dot product of the first row and this vector. Then we have the second element has to be equal to the second row by vector, and so on and so on. So I can write another example. So now we can use only numbers in both matrix and vector. So after multiplication of a matrix by a vector, we have the result is a vector, and as I said earlier, the first element, the first component of the resulting vector is the first row times the vector. So it will be 1 times 2 plus 2 times 3 and 3 times 1. Then we have the second row, so it is 4 by 2, 4 times 2, plus 2 times 3, plus 1 times 1. And the last row is 0 times 2, plus 5 times 3, plus -1 multiplied by 1. Okay, so we have 2 plus 6 is 8, plus 3 is 11. Then we have 8 plus 6, which is 14, plus 1 is 15. And then we have 0 plus 15 minus 1. So that's the result of this multiplication. And as we know that the left side of the system of linear equations can be written also as a linear combination, so we can write also that, so I will write another example. And this is the same as the first column of this matrix, so it is 1, 4, 0, multiplied by the first component of the vector, so it will be times 2. Then the second column, it is 2, 5, 2, 2, 5 times 1. And finally, we have 3, 1, 3 multiplied by the third component of this vector. And then we can multiply these vectors by these numbers. So it will be 1 times 2 is 2, 8, 0 plus 2, 2, 5 plus 9, 3, 9. The result is 2 plus 2 plus 9. So it is 9 plus 4 is 13. 10 plus 3 is also 13. And 5 plus 9 is 14. Okay, so you can, so please try to try to remind that this is a linear combination. Okay, and so we can say that matrix is an array of numbers. So in this case, we have an example of square matrix. So it has the same numbers of rows and columns. So we can say that matrix A, we typically denote matrices with boldface uppercase letters. If we have 1, 2, 3, 4, 2, 1, 0, 5, 3, we can also write that A is in the set of matrices 3 by 3. And the first dimension of it is the number of rows, and the second dimension is the number of columns. So we can write that matrix 1, 2, 3, 5, 4, 0. So we can write that this will be matrix B, and B is in the set of matrices of dimensions 2 by 3, 2 rows and 3 columns. And if we want to refer to a certain element of this matrix, to a certain entry of this matrix, we can write, for example, that the element in the second row and, let's say, first column is 5. Okay, so we can write it like this. Yes, so I think that we can start with this first the first task, which is in the new PDF that I uploaded that I have uploaded today. It is called matrices, and in this first task we have to compute several products. So we can start with this. We have 4, 0, 1, 0, 1, 0, 4, 0, 1, and this is multiplied by 3, 4, 5. So we have 4 times 3 plus 0 times 4 plus 1 plus 5. Maybe in this first component I will write all these operations. So it will be 4 times 3 plus 0 times 4 plus 1 times 5. Okay, then we have 0 times 3 plus 1 times 4, which is 4, plus 0 times 5. And in the last row, we have the same entries as in the first row, so it will be the same. So we can actually write that we have 4 times 3 is 12, plus 1 times 5 is, so 12 plus 5 is 17. So finally, will be 17, 4, 17. The second example is very important because it shows important matrix called identity matrix. So it's like 1 in a number. So if you multiply a vector by this identity matrix, it won't change this vector. So the result will be 5, -2, and 3. Finally, we have the last, we have this example with 2 by 2 matrix multiplied by 1, 1, and then we have 2 and 4. So if we multiply matrix by a vector by a vector which whose all components are equal to 1, we will obtain another vector which will have sums of coming from each row. Okay, so the first component is the sum of entries in the first row. The second component is the sum of the entries from the second row. Okay, I will check if you have any questions. And in the second task, we have to write products as linear combinations of columns of these multiplied matrices. So in the first example, we have matrix 4, 5, 6, 1, 1, 1. Okay, and we have to write it as linear combinations. So the first column, 4, 5, 6, is multiplied by sorry, it's multiplied by 1 plus 1, 1, 1 is multiplied by 3. So then we have 4 plus 3 is 7, 5 plus 3 is 8, and 6 plus 3 is 9. In the second example, we have matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we want to multiply a matrix by a vector, the number of columns of this matrix have to be the same as the number of components. Otherwise, it is not possible to do such a multiplication. So in this case, we have 1, 4, 7 multiplied by 0 plus 2, 5, 8 times 1 plus 3, 6, 9 multiplied by 0. So actually, the result will be the second column of this matrix. So 2, 5, 8. So if we have a vector whose elements, whose components are zeros except one, which is 1, then it is like extracting a certain column from this matrix. So if we have only one non-zero element and its value is 1, then we will extract the second column from this matrix. And the last example in this second task is 4, 6, 8. Multiply 3, 6, 9. And we have two components, 1 over 2 and 1 over 3. 4, 6, 8. Three, 6, 9 times 1 over 3. So it will be 2, 3, 4 plus 1, 2, 3. Okay, and if we have a matrix with one row, so it's actually a sequence of numbers. So I moved to this exercise number 3. This is like writing a dot product of these two vectors with the same components. So the result is 1 times 1 plus negative 2 times negative 2 plus 7 times 7. So it's 1 plus 4 plus 49. So it's 54. Then we have the second example, 1 minus 2, 7, 3, 5, 1. And it is 3. minus 10 plus 7, it's 0, so it means that these two vectors are orthogonal, are perpendicular, and the last example is different because first we have a vertical vector multiplied by horizontal vector, and I haven't provided you a definition of multiplication for this kind of vectors. Anyway, I will show you now how to multiply it. So in this case, the result will be a 3 by 3 matrix, and we multiply, and each entry of this matrix, of this resulting matrix, is are just the dot products or just products between rows and columns of these two matrices. So rows of the first matrix and columns of the second matrix. So the first entry will be 3 times 1 is 3. Then we multiply 3 times negative 2, so it will be minus 6, and 3 times 7, which is 21. And we have 5 times 1, 5 times negative 2, which is minus 10, and 5 times 7, which is 35. And in the last row, all components of the second vector will be multiplied by 1. So we'll have 1, negative 2, and 7. So now I think that we can move to rules of multiplication of matrix by matrix. So there are several ways to describe these multiplications. So if we have a matrix, let's say 1, 2, 3, 4, 5, 2, 1, 0, 3. And we can, for example, multiply it by a matrix which is 3 by 2. So now we can say, as in the previous example, that each entry of the resulting matrix is a dot product of rows of a certain row and of the first matrix, so of the left matrix, and the column of the right hand matrix. So 1, 1 entry of the resulting matrix is a dot product is the dot product of the first row and of the left hand side matrix and the first column of the right hand side matrix. So I will write all these computations that are needed to find this first entry. So it will be 1 times 1, then 2 times 4, plus 3 multiplied by 1. The second element in the first column will be second row of the left-hand matrix times first column of the right-hand matrix. So it is 4 times 1 plus 5 times 4 plus 2 times 1. Okay. And 5, okay, 4. And the last element in the first column is the third row times the first column. So it is 1 times 1 plus 0 times 4 plus 3 times 1. And we have also the second column of the result. So we can multiply the first element in the second column is the first row times the second column. So it will be 1 times 2 plus 2 times negative 1 plus 3 times 2. And we have 4 second row times the second column. So 4 times 2 plus 5 times negative 1 plus 2 times 2. And the last entry is 1 times 0, 1 times 2 plus 0 and plus 3 times 2. Okay, so we can calculate all these entries. So the first entry, 1 entry is 1 plus 8. So we have 9 plus 3 is 12. And we have 4 plus 20, so 24 plus 2 is 26. 1 plus 0 plus 3 is 4. And the second column is 2 minus 2 is 0 plus 6. 8 minus 5 is 3 plus 4 is 7. And 2 plus 6 is 8. So that's the result. And we can write this rule of matrix-matrix multiplication. So let's say that we want to multiply matrix A, which is m times k. And the second matrix will be k times n, so k rows, n columns. And if we want to compute the element in the ith row and jth column of the resulting matrix C, we need to do the computations. So let's say L from 1 to k, and it will be A I L times B in the lth row and jth column. And we need to do it for I, which is from 1 to m, and j, which is from 1 to n. So if we have matrix, we want to multiply a matrix which is m times k, so m rows, k columns, times k times n. So these two have to be equal, otherwise we will not able to multiply such matrices. So if they are equal, we can multiply it, and the result will be m by n. So in this case, we have 3 by 3 matrix. Okay, so I can 3 by 3 matrix multiplied by 3 by 2 matrix. And these two dimensions are equal, and the resulting matrix has 3 rows and 2 columns. So yeah, so it's okay. So that's the one possibility of describing this multiplication. So in all cases, we can describe multiplication of two matrices using this formula, but I would like to show you that if you multiply two matrices, where you can find linear combinations in these this kind of operations. So let me write the same matrix. So it is 1, 2, 3, 4, 5, 2. Then we have 1, 0, 3. It is multiplied by 1, 4, 1. It was 2, negative 1, 2. So another way is to show that each column of the resulting matrix is a linear combination of the columns of this matrix with coefficients from the right-hand matrix. So I will use this non-standard notation. So the first column of the resulting matrix will be a linear combination of columns of this left-hand matrix with coefficients from the first column of the second matrix. So the first column is 1, 4, 1. So actually, both columns of the resulting matrix will be combinations of the same columns, so columns of the left-hand matrix. It is 3, 3, 2, 3. Two, 5, 0, and 3, 2, 3. Okay, and in the case of the first column of the resulting matrix, the coefficients are of this linear combination are 1, 4, 2, and for the second column will be 2, negative 1, and 2. So we can multiply and add all these numbers. So the first row, the first column is 1 plus 8 plus 6. So 9 plus 6 is 15. And then we have 4 plus 20, 24 plus 4 is 28. Then we have 1 plus 0 plus 6, which is 7. And the second column is 2 minus 2 plus 6. We have 8 minus 5, which is 3, plus 4 is 7, and 1 plus 6 it is 2. 1 times 2 plus 6 is 8. So it should be the same. It is 20. I've made a mistake. Let me check 452103. You probably 141 250 142. And we have 1 4. So we should have 1 plus 8. Yeah, it should be. Yeah, 1 plus 8, which is 9, plus 6 is 15. So I made a mistake earlier because we have 1 plus 8, 9 plus. Okay, so I've made a mistake by writing this number. So it should be 1. So I think that I will leave this as it is because now it is correct, although my first intention was to write the same product of matrices. Okay, and so you can try to remember that each column of the resulting matrix of matrix multiplication is a combination of columns of the left-hand matrix, and another way of a description is that each row of the resulting matrix is a combination of rows but the right-hand matrix. So we can use the same two matrices. So we have 1 2 3 4 5 2 1 0 3 1 2 4. Okay, so each row of the resulting matrix is a combination of these 3 rows. So we have 1 2 4 negative 1 and 2 2. And I can rewrite it for each row. And then we can use coefficients from rows of the left matrix. So for the first row of the resulting matrix, the coefficients will be 1 2 3. Four, 5, 2, and then we have 1 plus 0 plus 3. And then you can make all these calculations. So the first element, first entry will be 1 plus 8 plus, so 9 plus 6 is 15. Then we have 1 times 2, which is 2, negative minus 2 plus 6. So the first row is okay. In the second row, we have 4 plus 20 plus 4, which is 28. And then we have 8 minus 5, which is 3 plus 4, 7, and then we have 1, 2, plus 6, 6, which is 7, 8. So I think that that you can remember these three kinds of to remember where you can find these linear combinations in matrix multiplication. And I think that it's a good time for you to try to make these multiplications from this task number 4. So we have 3 matrix multiplications, and I will give you several minutes to try to multiply it and maybe remember these rules of multiplication, and then I will also do some of them by myself. So yeah, I will be back in, let's say, 5 minutes. Okay, so I will try to do these examples from this exercise number 4. So the first one is with matrix 1, 1, negative 1, 2, 3, negative 2, multiplied by 1, 0, 1, 1. So the 1, 1 entry is the first row times the first column, so it is 1 times 1 plus 2 times 1, so 1 plus 2 is 3. Then the second element in the first column, second entry in the first column is the second row times the first column, so it is 1 times 1 plus 3 times 1, so 1 plus 3 is 4. And finally we have negative 1 plus negative 2, it will be negative 3. And the second column is will contain these dot products of rows and the second column of the right hand matrix. So it will be 1 times 0 plus 2 is 2, 1 plus 0 plus 3 is 3, and we can notice that it is vector. The second column contains 0 and only 1, so it is like extraction of the second row of this matrix. So we can write it like this. So that's the result of this first example. And we have also to, in this text for task number 4, we are also asked to write them as linear combination of columns, and I guess there should be rows. So if we want to write it as linear combination of columns, we can write that the first column is the linear combination of 1, 1, negative 1, and second column of the left-hand matrix, so it will be 3, 2, negative, and for the first column, the coefficients of this linear combination will be 1, 1, while for the second column, it will be the combination of the same columns, but with different coefficients, 0 and 1. And if we want to write it as a linear combination of rows, so each row of the resulting matrix is a linear combination of two rows, 1, 0, and 1, 1. So in the first row, the coefficients are 1 and 2. In the second row, it is 1 and 3. And okay, and maybe I will skip the second example, and I will try to do also the first example in this task, in this fourth task. So it is, let's clear it. 1, 1, 1, 2, 0, 1, 0. So the result will be 2 by 3 matrix, as we have 2 times 2 by 3 times 3 by 3. So the resulting so the shape of the resulting matrix will be 2 by 3. So we have the first row times the first column. So it is 1 plus 0 plus negative 1. So it will be 0. Then the second row times the first column. So it will be 2 plus 0 plus 0 will be 2. Then we can move to the second column. So the first entry in the second column is the first row times the second column. So it is 1 plus 1 plus 0. So it will be 2. And then we have 2 minus 1 is 1. And in the last column, we have negative 1 plus 0 plus 1 is 0. And negative 2 plus 0 plus 0 is negative 2. So that's the result, and you can also try to write it as a linear combination of columns and rows, but I think that we can skip it because we don't have so much time. And I think that we can move to task number 7, where we have there are given dimensions of 4 matrices, A, B, C, and D. So we know that matrix A has dimensions 3 times 5. Matrix B is 5 times 3. Then we have matrix C, which is 5 times 1, and matrix D, which is 3 times 1. And all entries in these matrices are 1. And which of these operations are allowed? By saying these operations, we mean which of matrix multiplications between which pairs of these ABCD matrices are allowed, and what are the results. So we can think of multiplication of A times A, and this one is not allowed because we would have 3 times 5 times 3 times 5, so it is not possible to multiply it. Then we have A times B, so we can draw this line, and then we have A times B, so 3 times 5, and then we have 5 times 3, so the result will be 3 by 3. So the resulting matrix will be 3 by 3. And can you write me in the chat what will be the entries of this this resulting matrix of product A and of matrices A and B? So as there are all ones, yeah. So this so these are dimensions, and each entry in this resulting matrix. What will be the value of all entries in this resulting matrix? Okay, I can't see answers, any answer. So yes, it will be, there will be all entries will have value 5. It's because we have 3 times 5, and we know that all entries in these matrices are ones. So each row in the left-hand side matrix has 5 entries equal to 1, and then we have 3 columns also containing only ones. So all dot products between rows and columns will be the same. So it is 5-dimensional vector with ones multiplied by 5-dimensional vector with ones. So all entries will be equal to 5. Okay. And is it possible to multiply A by C? So in this case, we can check it. We have 3 times 5 times 5 times 1. So yes, it's possible, and the resulting matrix will be 3 times 1, and all components of this resulting vector will be equal to 5. Okay? So how about this A times D? In this case, we have 3 times 5 multiplied by 3 times 1. So no, it's not possible. And so we can move to B times A. So in this case, we have B, so it is 5 times 3 multiplied by 3 times 5. So this operation is allowed. The resulting matrix will be 5 by 5. And what will be the value of all entries of this in this matrix, in this resulting matrix? Yeah, so now we will obtain matrix 5 by 5 with all entries equal to 3. And so on and so on. Okay, then we have B times B. So this one is not allowed. So we can try B times C. B times C. So 5 times 3 times 5 times 1. It is not allowed. And then B times D. This one is allowed. So 5 times 3, 3 times 1. So the resulting matrix, and so actually it will be a vertical vector with 5 components, and all components are equal to 3. And then C times A is not possible to do. C times B is also not allowed. C times C is not allowed. C times D is not allowed. And D times A, it's not allowed. Then we have D times B. So yes, so I think that we we've done all these operations that are allowed here. And one comment that I want to give you is just to remember that this matrix multiplication is not commutable. So A times B is not the same as B times A. Okay, so you can obtain different results, actually even different dimensions of the resulting matrix if you try to multiply these matrices with different order. Okay, and yes, so we have 25 minutes left. Yeah, I think that we can try to do task 8. So what rows or columns of matrices do you multiply to find the third column of AB, for example? So in this case, I can, if I want to find the third column of AB, I need to multiply matrix A by the third column of matrix B, because I know that only these entries from the third column of matrix B will be used to compute the third column of the resulting matrix. So there are these coefficients of linear combinations of columns of matrix A. So we can write that in the case of the third column of A, B, we multiply matrix A by third column of B. So how about the second example, when we want to compute the first row of AB? What do we need to multiply? If we want to find the first row of AB. Please write it in chat if you know. Yes, so it will be the first row of A times B. Okay, so we can write first row of A times B. And how about C? So the entry in the third row and fourth column of AB. So what do we need to multiply? So we need element 3, 1 of AB. Third row times fourth column. Okay. And finally, we have this CDE matrix. So we want to find the entry in the first row and first column of CDE matrix. So what do we need to multiply in this case? Okay, so maybe I will help you with it. So actually, you can check it later, but it will be first row of C times D times first column of E. Okay, so in this result, all elements, it will be dependent of all elements of matrix D, and only first row of C and first column of E. Okay, then we have this task number 9, and it says about where this distributive law is checked. So yes, I haven't told you about this addition of matrices, but actually it is just adding of corresponding entries. And now in this task number 9, I will give you an example of such operation. So we need to check if A, B plus C is the same as A, B plus A, C. So we have these matrices A, B, and C. And first we can try to do this left-hand side. So we have A, B plus C. So it is 1, 5, 2, 3 times 0, 0, 2, 1 plus 3, 1, 0, 0. So it's 1, 5, 2, 3. Then we have 0 plus 3 is 3, 2 plus 1 is also 3, 0 plus 0 is 0, and 1 plus 0. So I've just added these corresponding entries. So 1, 1 to 1, 1, 1, 2 to 1, 2, and so on. And then I have to multiply these two matrices. So the result will be 2 by 2 matrix. And we have 3 plus 0, which is 0, 3 plus 5, which is 8. Then we have 6 plus 0 is 6, and 6 plus 3 is 9. Okay, I will check it again. So we have 6 plus 0. I think that it's correct. And then we can also compute A times B, 1, 5, 2, 3, multiplied by 0, 2, 0, 1. So if we have both coefficients of linear combination that are 0, we know that the first column will be also 0. And then we have the second column. It is 1 times 2 plus 5, so it's 7. And then we have 4 plus 3, which is also 7. And then we have to multiply A times C. 1, 5, 2, 3, multiplied by 3, 1, 0, 0. Then we have 3 plus 0, which is 0. 1 plus 0, which is 1. Then we have 6 plus 0 and 2 plus 0. Okay, and then if we add these two matrices, so I will not rewrite it again, but just will draw it like this, that I want to add these two matrices. So I have 0 plus 3 is 3, 7 plus 1 is 8, 0 plus 6 is 6, and 7 plus 2 is 9. So these two matrices are equal. So that's how we have shown that at least in this case this distributive law works, but actually it works for all matrices that are with dimensions that are low for computations. And we can also check this associative law, because matrix multiplication is associative. So A times BC is the same as AB times C. But I think that you can try to do it by yourself. How much time do we have? Yeah, so we have about 14 minutes. So yes, then this task number 10 is good to do. So where we have to try these different powers of A. So maybe I will check for this first matrix. So the matrix A is 1, B, 0, 1. And if I want to obtain A squared, is the same as 1B 0, 1 multiplied by 1B 0, 1. Okay. And yes, so in this case we have, as this is 1, 0 in the first column of the right-hand matrix, it means that 1, 0 should be in the first column of the resulting matrix. And then we have 1 times B plus B times 1, so the result will be 2B, and then we have 0 plus 1. And if we want to obtain the third power, so it will be the same as A squared times A. So we know that A squared is 1 2B 0, 1 multiplied by 1B 0, 1. So the first column will be 1, 0, and the second will be B plus 2B, so it will be 3B. So for the next powers, we will always add another B to this element, and then we have 0, 1, 0, 1, so it means that it will always stay the same. So the second row and the first column will always stay the same, but if we take greater and greater powers of A, which each increment in power will result in increment of this number. So if we want to take nth power of A, it will be 1 and B 0, 1. So that's the result, and you can also try to do similar task for the second matrix. And then task number 11, where we choose the only B. So for every matrix A, so we need to find 3 by 3 matrix that that satisfies these examples. So in the first example, we know that matrix A is also 3 by 3. So we want to find matrix B such that this equation is satisfied for all 3 by 3 matrices A. So do you have any idea how B should look like? So we need a matrix B that will act in the same way as number 4. If you have any idea, please write it in the chat. Yes, like identity matrix, but with 4 instead of 1. It's because we can write that this is the same as 4 times I times A, okay? Because I times A, identity matrix multiplied by A, is the same as A. So if because of this associative rule, we can write 4 times I, so 4 times 1, 0, 0, 0, 1, 0, 0, 0, 1, which is 0, 0, 4, 0, 0, 0, 4. So I think that you can try to do the rest of these in a similar way. The rest of these examples from this exercise number 11. Then we have exercise this task number 12, where which of the following matrices are guaranteed to equal A minus B squared? So you need to remember that this matrix multiplication is not commutative, so it's not A squared plus minus 2AB plus B squared, but you need to treat AB and BA as potentially different matrices. Okay, so you can actually, because of this distributive law, you can multiply A minus B, so it is the same as A squared, A minus A times B minus B times A plus B squared, and compared this, and you can compare this expression with these expressions listed in task 12. And how much time do we have? So yes, I think that you should be able to do also this exercise 13. And now I would like to do these 3 exercises 14, 15, and 16, because these 14 and 15, they lead to computations for inverse matrices. So last time we tried to do this Gauss elimination method, and it was written using the standard systems of linear equations notation, but you can use more compact notation using augmented matrix by using augmented matrix. So we want to find this to solve system of linear equations that is now written with matrix and vectors. So matrix A has these components 1, -2, 1, 2, -2, 0, -1, 4, and 0. Okay, B has these 3 entries, and X will contain 3 unknowns. Okay, so and we can use this notation. We can use augmented matrix to solve in very similar way as previously the system of equations. So we can add this vector components of this vector B as a fourth column of a new matrix. So the first 3 columns are the columns of matrix A. And we can do this Gauss or Gauss-Jordan method by using only these coefficients. So actually what we did last time, but we just used this compact notation. So the first thing what we need to do is to use this pivot and to eliminate 2 and 1 that are below this pivot. So we need to subtract from the second row. We need to subtract the first row multiplied by 2. So we have 2 minus 2 is 0. Then we have minus 2 minus, so will be plus 4. So, and then we have 0 minus 2 and 0 minus 0. And in order to eliminate this -1, we need to add the first row to the last row. So we'll obtain 0, 2, 1, and 3. And the next pivot is this 2 by 2, 2, 2 element. So we need to eliminate entries below this pivot. So we can rewrite first 2 rows unchanged. And then we can subtract the second row from the third row. So the result will be 2 minus 2 is 0. Then we have 1 minus minus 2. So it will be 3 and 3. So now we can multiply the first row or divide the third row by 3. And use back substitution, or we can continue with elimination. So in order to, so we can use this number as pivot and eliminate everything above it. So it will be 0, 0, 1, 1. Then we can multiply the third row by 3 and add it to the second row. So it will result with 0, 2, 0, 3. And then okay, is it? I think that I made a mistake here because, yeah, it is -2, and I don't know why I rewrite it as -3. So in this case, I need to multiply the third row by 2 and add it to the second row, and then I think that numbers will be much better. And we need also to eliminate this entry, so we need to subtract the third row from the first row, so it will be 1, -2, 0, -1, and finally we use this pivot to eliminate the number, the entry above it, so we need to add second row to the first row, so the result will be 1, 0, 0, 1. We can divide the second row by 2, so now we can read the result of we can read the solution of this matrix from this augmented matrix from the last row, from the last column of this augmented matrix. So it means that X has 3 components equal to 1. And of course, we can check if it's correct. So if we multiply A by X, we should obtain B. So we have 1. So actually, as all components are 1, we just need to check if sums in all rows are the same as these numbers. So if we sum all entries in the first row, we have 1 minus 2 plus 1 is 0. Then we have 2 minus 2 plus 0 is 0. Minus 2 plus 4 is 3. So it seems that it's okay. And then we have this. Let's check how much time do we have. Yeah, it seems that it's after 3, so I think that I will finish this example next time. So thank you for your attention, and see you next Wednesday.